All right, chapter 11 is all about intermolecular forces. So with this problem, we're supposed to identify the different attractions between the different molecules. So looking at one, we have two hydrogen fluoride molecules. When you have hydrogen fluoride, a hydrogen bonded to a fluorine, you have a situation where you have H bonding. Because fluorine is so electronegative, same with oxygen, same with nitrogen, the electrons get shifted all the way over towards the more electronegative element, the fluorine. So instead of being a run-of-the-mill dipole-dipole interaction, right, of two polar molecules attracting each other, this is kind of a super strong one. So they call this dipole-dipole attraction a hydrogen bond. Now, be clear, it's not a bond. The bond is the stick between the hydrogen and the fluorine. That's way harder to break than the interaction between the negative side of HF and the positive side of the other HF. So hydrogen bonds are way weaker than covalent bonds, but they're strong for dipole-dipole interactions. If we're looking at situation 2, these are two fluorine molecules, right? This is a non-polar molecule. So all you have left when you have non-polar molecules is what are called dispersion forces. Electrons, just through random motion, right, even though it's a non-polar molecule, can end up more on one side than another. This is called an induced dipole. This can in turn shift the electrons in the other molecule, so you have an induced dipole. And then you get a little tug between the two molecules. All right, this is called a induced dipole attraction, or a dispersion force. With 3, you've got a positive cation, and you've got the negative side of water interacting with the positive cation. We call this an ion dipole attraction. All right, so this would be a strong attraction because you've got a positive thing attracted to the negative side of water. Anytime you have a polar molecule, they have a dipole-dipole attraction, right? Two polar molecules line up with each other, so the negative side of the one molecule is attracted to the positive side of the other molecule. So I don't know, I feel compelled to emphasize, right? Dipole-dipole interaction is just a polar molecule interacting with a polar molecule. Special is hydrogen bonding, right? Because it's a very strong dipole-dipole interaction because oxygen is so much more electronegative than the sulfur. So you get a real shift in the electrons over towards the oxygen and away from the hydrogen. So hydrogen bonding is anytime you have an OH group, right? So with ethanol, we've got an OH group, so the ethanols line up so that the hydrogen on the one hydrogen-oxygen bond lines up with the oxygen of the other hydrogen-oxygen bond. And this is what constitutes hydrogen bonding, or that special kind of dipole-dipole attraction. Induced dipole attractions or dispersion forces are the weakest. All right, so they can have a cumulative effect where a whole bunch of induced dipole attractions add up, but isolated by itself, it's a weak attraction. All right, 3. Do you expect the viscosity, right, how fast glycerol flows, to be larger or smaller than that of one propanol? Explain. All right, so looking at the molecule glycerol, I can see 1, 2, 3 OH groups, whereas with propanol I have one OH group. So the more OH groups you have, the more potential you have for hydrogen bonding. So I expect glycerol to be more viscous because it has more OH groups capable of more hydrogen bonding. 5. Using the graph of carbon disulfide data, determine the vapor pressure of carbon disulfide at 30 degrees Celsius. All right, so anywhere where you touch the red line is where you have this interface between the liquid phase and the gas phase of carbon disulfide. So at 30 degrees, we touch the line, I don't know, my eye sees about, 390 millimeters of mercury, right? Somebody could have seen 380, I guess. So at 30 degrees Celsius, my estimate is a vapor pressure of 390 millimeters of mercury. At the temperature at which the vapor pressure equals 300 torr. All right, so looking at the vapor pressure side, right, going up the y-axis at 300, I touch the line less than 30 degrees, I don't know, greater than 20. I said about 20, about 22. All right, well, maybe that's a little off, but that's my estimate, right? At 22 degrees Celsius, this is what the vapor pressure of this molecule would be. And normal boiling point, all right, so we boil when the vapor pressure is equal to the atmospheric pressure, so normal is 760. So we're touching the line at 47 degrees Celsius roughly. So 47 degrees Celsius, this molecule boils at 47 degrees Celsius. Number 6, the molecules propanol and ethyl methyl ether have the same molecular formula. Let's see, same molecular formula but different constitution. So they have different boiling points, right? Propanol boils at a much higher temperature than ethyl methyl ether. Rationalize the difference between the boiling points. Well, I can see that OH group sitting off of there. All right, so if you got an OH group, you're capable of hydrogen bonding, and that would be the reason why you would have such a high boiling point. Ethyl methyl ether is a polar molecule capable of run-of-the-mill dipole-dipole interactions. All right, reading a phase diagram. Phase diagram plots pressure versus temperature. At a particular temperature and a particular pressure, either fall into one of three zones. The solid phase, the liquid phase, or the gas phase. And these zones are delineated by boundaries, right? Each of the boundaries would represent either freezing point, boiling point, or sublimation point. So estimate normal boiling and freezing point of a substance. So normal is 1 atmosphere pressure. So if I draw a line across 1 atmosphere pressure, wherever it touches the interface between the different phases, looking at where it touches the blue line, which is the interface between the solid and the liquid phase, that's freezing point. So I'm saying about 260 Kelvin for the freezing point. And wherever it touches the red line would represent, at a particular pressure, at a particular temperature, the boiling point. So I see 360 for the boiling point. What is the physical state of the substances under the following conditions, right? So at a particular temperature, at a particular pressure, if you're not hitting the cusp between changing from one phase to another, you're in a phase. So if we follow I across, pressure of 150 and 0.2 atmospheres, you're landing in the gas phase. If we plot 100 Kelvin versus 0.8 atmospheres, you're landing in the solid phase. And if we plot 300 Kelvin, 1 atmosphere, you're landing in the liquid phase. So that's how you read this chart. C, what's the triple point? The triple point is an interface, or the point, where all three phases are represented at the same time, right? You're partly in the solid phase, partly in the liquid phase, partly in the gas phase. So that's this point right here. So less than 200, about 190 Kelvin and 0.45 atmospheres. I'd say that's the triple point. Arrange the substances, carbon tetrachloride, silicon, and argon, increasing boiling point. Stronger the molecular attraction, the harder it is to boil, the higher the boiling point. So I can see right off that with silicon, solid silicon is held together by covalent bonds. So solid silicon is like sand. You'd have to get it up to thousands of degrees Celsius if you wanted to melt sand. Whereas carbon tetrachloride is a molecule. So in the solid phase, you'd have molecules at the lattice point. So you're being held together by some sort of van der Waals attraction. And since it's nonpolar, it'd be dispersion forces, so very weak attraction. So it'd be very easy to melt carbon tetrachloride. Even easier would be argon. Argon's a very non-polarizable atom, so it would have very weak dispersion forces between argon. So very hard to solidify argon, very easy to melt it, easy to boil it, easy to get in the gas phase. Also, molar mass plays a part, right? So the heavier the molecule is, the harder it is to get into the gas phase. So higher boiling point with carbon tetrachloride because it's more polarizable and it's heavier.